Hello there, and welcome to the Sleepy Space Channel. Tonight, a quiet correction to one of the most dramatic images the night sky has ever offered us. Somewhere above you, depending on the season and the hour, there is a faint smudge of light, visible without a telescope on a clear, dark night. A smudge that has been watched by human eyes for as long as there have been human eyes to watch it. That smudge is the Andromeda Galaxy, the nearest large galaxy to our own. And for most of human history, it was simply a curious patch of light, unexplained, unremarkable, one smudge among the thousands of points and patches that fill the dark. What we now know about that smudge is something far stranger than anything our ancestors could have guessed. Andromeda is not simply nearby. It is approaching. It has been approaching for a very long time. And in a sense, that will take the rest of tonight to properly unpack. It may already, in the gentlest and least violent sense imaginable, be touching us. Tonight we will walk through what a galaxy collision actually is, why the word collision is almost the wrong word entirely, what is already happening above your head, whether or not anyone notices, and what the very distant future holds for the small stretch of space that you currently call home. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to hold. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Begin with the image that the word collision naturally summons. Two galaxies, each containing hundreds of billions of stars, approaching one another across the dark, and then, at some appointed moment, crashing together. The mind fills in the rest almost automatically. Stars slamming into other stars. Explosions. A sky lit up with catastrophe. This is the image that illustrations tend to reinforce. Two great spiral disks shown overlapping, edges tangled together. The suggestion of violence implicit in the very word collision, a word borrowed from the world of cars and billiard balls, and things that crunch and shatter on contact. Almost none of this is what actually happens when two galaxies meet. And the reason it is not what happens has everything to do with a fact we have touched on before in this channel. A fact about emptiness, about the staggering amount of space that separates objects, even within structures that look, from a distance, crowded and continuous. If the asteroid belt, despite containing hundreds of millions of objects, is mostly empty space, then a galaxy, containing hundreds of billions of stars, is empty space on a scale that makes the asteroid belt look like a packed room by comparison. And when two such enormous volumes of mostly nothing pass through one another, the nothing simply continues to be nothing, for the most part, while something else entirely, something slower, stranger, and in its own way far more interesting than a collision, unfolds instead. Worth a few unhurried sentences here is the actual scale of emptiness inside a galaxy, because this number is the foundation for everything else tonight. The Milky Way contains, by current estimates, somewhere between 100 billion and 400 billion stars. A number that large is already difficult to hold in the mind, but the more important number is not the count of stars. It is the space between them. The average distance between stars in the part of the galaxy where the sun resides is several light years. The nearest star to the sun, as mentioned in earlier explorations of this channel, is a little over 4 light years away. A light year, recall, is the distance light travels in a full year, moving at 300,000 kilometers every second. a distance of nearly 10 trillion kilometers. Now consider the stars themselves. The Sun, an entirely typical star, is about 1.4 million kilometers across. The distance to the nearest star is, in the same unit, about 40 trillion kilometers. If you take the ratio of the size of a star to the typical distance between stars, you arrive at a number so small that it becomes almost meaningless to express as a percentage. If the Sun were shrunk down to the size of a single grain of sand, the nearest other grain of sand, representing the nearest star, would be many kilometers away, somewhere in the next town over. And the space in between, all of that distance, all of those kilometers, would be entirely empty. No other grains of sand at all. This is the actual texture of a galaxy. Not a crowded disk of light, but an almost perfectly empty volume of space, with occasional, vanishingly rare points of matter scattered through it, so far apart from one another that from the perspective of any single star, its nearest neighbors are still profoundly, overwhelmingly distant. A galaxy, despite containing hundreds of billions of stars, is by volume more empty than the emptiest vacuum chamber ever built on Earth. The stars are there, but the space between them dominates everything, the same way the space between asteroids dominates the asteroid belt, only multiplied by a factor that is difficult to even write down. Now bring two such structures together. The Milky Way and Andromeda are each enormous disks of stars, each one mostly empty space, punctuated by the same kind of vanishingly rare points of matter just described. When these two disks eventually overlap, when the stars of one galaxy begin to occupy the same general volume of space as the stars of the other, the overwhelming likelihood for any individual star is that nothing happens to it at all. Its neighborhood, already almost entirely empty, simply becomes the neighborhood of a slightly different set of equally distant, equally invisible neighbors. The star continues on its orbit around its own galaxy's center, now influenced by a slightly different overall gravitational landscape. But it does not strike another star. It does not even come close, in any way that would be noticeable on a human timescale, or indeed on almost any timescale at all. Calculations of how many actual star-on-star collisions are expected during the eventual merger of the Milky Way and Andromeda produce numbers that are, by galactic standards, vanishingly small. Out of the hundreds of billions of stars in each galaxy, the expected number of direct stellar collisions is essentially zero, or close enough to zero that astronomers describing the event tend to phrase it as exactly that. Two galaxies, each containing hundreds of billions of stars, can pass through one another, can merge entirely into a single structure, and in doing so, produce a number of actual star-on. This is the first and largest correction to the popular image. The word collision, in the context of two galaxies, does not refer to stars hitting stars. It refers to something else entirely, something gravitational, something that unfolds not in moments, but across spans of time so long that the word collision, with its connotation of suddenness, of impact, of a single decisive instant, is almost the opposite of what is actually happening. What is actually happening is closer to two enormous slow tides, each one made of mostly empty space with a scattering of stars, gradually flowing into and through one another, rearranging themselves over hundreds of millions of years, guided not by impact but by gravity, the same patient, accumulating force that shapes spiral arms and asteroid belts and everything else this channel has explored. Turn now to Andromeda itself, because before going further, it is worth understanding what exactly is approaching and how we know. Andromeda, formerly catalogued as a spiral galaxy, not unlike our own, sits at a distance of approximately 2.5 million light-years from the Milky Way. This number deserves the same kind of careful unpacking that the distances within the Orion Arm received on a previous evening. 2.5 million light-years means that the light currently arriving at your eyes, on any clear night when Andromeda is visible, left that galaxy 2.5 million years ago. 2.5 million years ago, the ancestors of modern humans were only just beginning to diverge from earlier hominid lineages. Early stone tools were just beginning to appear in the archaeological record, and the climate of Earth was entering a long series of ice ages that would shape the next several million years of the planet's history. The light you see tonight, if you happen to look up and find that faint smudge, began its journey before any of that had happened. It has been traveling, uninterrupted, through the emptiness between galaxies, for the entire span of human evolutionary history. And it is arriving now, similar to the Milky Way in structure, a barred spiral galaxy with a central bulge, a disk, and spiral arms, though somewhat larger. Estimates of Andromeda's size vary, depending on exactly how the edge of a galaxy is defined, a question that turns out to matter enormously for tonight's exploration. But in terms of its visible disk of stars, Andromeda is generally considered to be somewhat larger than the Milky Way, containing, by some estimates, roughly 1 trillion stars, several times the population. For most of the history of astronomy, Andromeda was simply a distant neighbor, beautiful, faint, occasionally studied, but not understood to be moving toward us in any meaningful sense. The discovery that it was approaching came from a technique already discussed in a previous exploration of this channel, the same technique used to determine the direction of the sun's motion through the local stellar neighborhood. The light from Andromeda, when its spectrum is carefully measured, shows a shift, and unlike the vast majority of distant galaxies, whose light is shifted toward longer wavelengths, toward the red, as the expanding universe carries them away from us, Andromeda's light is shifted toward shorter wavelengths, toward the blue. A blue shift, rather than a red shift, indicates motion toward the observer, rather than away. Andromeda is approaching the Milky Way at a relative velocity of roughly 110 kilometers per second. This number, on its own, sounds enormous, and in human terms it is, faster than any spacecraft humanity has ever built. But set against a distance of 2.5 million light-years, even a speed of 110 kilometers per second translates into an approach that will take, by most current estimates, somewhere in the range of 4 to 5 billion years before the two galaxies begin to interact significantly. 4 to 5 billion years is comparable to the entire age of the solar system. Up to this point, the Sun and Earth have existed for about 4.5 billion years. The approach of Andromeda, even at a speed faster than anything humanity has ever built, will take roughly that same span of time again before anything resembling an interaction begins. This brings us to the second wrong turn worth examining, and it is the heart of tonight's title. The popular framing of the Andromeda situation tends to present it as a distant future event, something that will happen eventually, in billions of years, a problem for some unimaginably distant descendant species, if any descendant species exists at all by then. And in terms of the visible disks of stars, the parts of each galaxy that show up in photographs, that framing is broadly accurate. The bright, star-filled portions of Andromeda and the Milky Way are still separated by an enormous distance and will remain so for billions of years. But galaxies, it turns out, are considerably larger than their visible disks of stars. Surrounding every galaxy, extending far beyond the region where stars are bright enough to be photographed, is a vast, diffuse halo made primarily of dark matter, the same mysterious component of the universe that has been inferred, though not directly observed, through its gravitational effects on the motion of stars and galaxies. This halo is not visible. It does not glow. It cannot be photographed in any conventional sense, but its presence can be detected gravitationally through the way it influences the motion of everything within and around it, and through more exotic techniques involving the way its mass bends the light of even more distant objects passing through it. The dark matter halo of a galaxy like the Milky Way or Andromeda extends to a radius far, far larger than the visible disk. Estimates for the size of these halos place their edges at distances of several 100,000 light-years from the galactic center, sometimes more, depending on exactly how the boundary of a halo is defined. A definition that, much like the boundary of the heliosphere discussed in the very first exploration of this channel, is not a sharp line, but a gradual fading, a region where the halo's density slowly decreases until it becomes indistinguishable from the background. When these halo sizes are compared to the distance between the Milky Way and Andromeda, something remarkable emerges. The 2.5 million light-year separation between the visible disks of the two galaxies is large compared to either disk individually, but it is not necessarily large compared to the combined extent of their two halos. Depending on which halo size estimates are used, and the uncertainties here are genuinely significant, the outer edges of the Milky Way's halo and the outer edges of Andromeda's halo may already overlap, may already be interpenetrating. Right now, tonight, in the most literal sense, while the bright disk of stars that we can actually photograph remains separated by millions of light years. Sit with this for a moment, because it is worth sitting with. The visible portion of Andromeda, the smudge of light visible to the naked eye, the disk full of stars that astronomers have studied for centuries, is still millions of light years away and will remain so for billions of years. In that sense, the popular framing, a distant future event, is correct. But the halo, the vast, invisible, dark matter-dominated structure that surrounds Andromeda and extends far beyond its visible disk, may already be reaching into the same volume of space that the Milky Way's own halo occupies. Two structures, each hundreds of thousands of light years across, each invisible, each detectable only through gravity, may already be overlapping, already exchanging some small gravitational influence, already, in the gentlest and most literal sense of the word, touching. This is not a claim that anything dramatic is happening as a result. The halos, even where they overlap, are themselves extraordinarily diffuse, far less dense even than the already nearly empty disk of stars described earlier. An overlap between two halos is not an event in any meaningful sense, not something that could be observed, measured, or felt by any single star within either galaxy. It is simply a geometric fact, a statement about the extent of two structures that happen, given current best estimates, to already extend far enough to share the same region of space. The collision, in the truest sense of the word, the actual beginning of two galaxies occupying overlapping volumes, may have already quietly begun, not with any event, not with any signal, but simply because the two structures involved are so much larger than the bright, photogenic disks that give each galaxy its name and its familiar appearance. Now turn to what will actually happen over the billions of years to come, as the visible portions picture that has emerged from detailed simulations, run many times with slightly different assumptions to explore the range of possible outcomes, is a picture of a process unfolding in stages, each stage lasting hundreds of millions of years, each stage involving not collision, but rearrangement, the slow reshuffling of two vast, mostly empty structures as their gravitational fields begin to overlap and influence one another. The first stage, expected to begin in roughly 4 billion years, involves the two galaxies making their first close approach, passing near one another, close enough for their gravity to noticeably distort each other's shape, but not yet merging completely. Simulations suggest that during this first approach, the two galaxies may actually pass by one another, swing past and separate again, before gravity eventually pulls them back together for a second approach. This is similar, in principle, to the way two objects on intersecting orbits might swing past each other, exchange momentum, and separate before their mutual gravity eventually brings them back together on a longer, slower timescale. During this first close approach, the gravitational distortion would be significant. The Milky Way's elegant spiral structure, the careful balance of density waves and rotation that has been discussed in previous explorations, would begin to be disrupted. Long streams of stars and gas, called tidal tails, would likely be pulled out from each galaxy. Vast arcs of material extending far beyond the original disk, drawn out by the gravitational pull of the approaching neighbor. These tidal tails are not speculation. They have been directly observed in numerous pairs of interacting galaxies elsewhere in the universe. Galaxies caught in the act of this same process, close enough to us, and at the right stage of their interaction for the tails to be photographed in detail. The Milky Way and Andromeda, billions of years from now, would likely develop similar tails, long curving streams of stars flung outward by the gravitational tug-of-war between the two approaching giants. After this first approach and separation, the two galaxies would eventually swing back together for a second, closer approach, and then likely a third, each one closer than the last, each one further disrupting the original spiral structure of both galaxies, until eventually, somewhere on the order of 5 to 7 billion years from now, the two would merge completely. Their stars, their gas, their dark matter halos, all combining into a single structure. What would this merged structure look like? Here, the picture shifts away from the elegant spiral shape that both the Milky Way and Andromeda currently display. Spiral structure, as discussed in the Orion Arm exploration, depends on a relatively calm, orderly rotation, density waves propagating through a disk in a stable, repeating pattern, the violent gravitational disruption of a merger. Even a merger, where no individual stars collide, is enough to disrupt this calm rotation entirely. Orbits that were once neat and roughly circular become stretched, tilted, randomized, as the combined gravity of both galaxies' stars and dark matter reshapes the orbital paths of everything within. The result, based on simulations and based on observations of other galaxies that have already undergone similar mergers, is not a spiral, but an elliptical galaxy, a roughly spheroidal or egg-shaped cloud of stars, with orbits oriented in many different directions, rather than the orderly, roughly coplanar orbits of a spiral disk. Elliptical galaxies, common throughout the universe, are thought by many astronomers to be, in large part, the products of exactly this kind of merger. Spiral galaxies, whose orderly rotation has been scrambled by gravitational interaction with another galaxy. The elegant pinwheel shape replaced by a more uniform, less structured cloud. The merged galaxy resulting from the Milky Way and Andromeda has somewhat informally been given a name by astronomers discussing this future event, a portmanteau combining the names of the two progenitor galaxies. This merged galaxy would be larger than either original galaxy, containing the combined stellar populations of both, an elliptical or possibly a disturbed spiral-like structure, depending on exactly how the merger plays out. Sitting where the Milky Way and Andromeda once sat separately, the two original galaxies no longer distinguishable as separate entities, their stars mixed together into a single, larger structure. Now turn to a question that is, for many people, the most immediately pressing one. Even though pressing is very much the wrong word for anything on this timescale. What happens to the Sun, to the solar system, to whatever world might exist on a planet like Earth during all of this? The honest answer, based on everything discussed so far about the emptiness of galaxies and the near impossibility of actual stellar collisions, is that the most likely outcome for the Sun and its planets is, in a sense, almost nothing. The Sun would continue to orbit within whatever structure it found itself part of, its immediate neighborhood of stars remaining roughly as empty and as quiet as it is now. The night sky, however, would change dramatically, not because of any danger, but because of the view. During the early stages of the interaction, as Andromeda's disk grows nearer in apparent size, the night sky would gradually transform. Andromeda, currently a faint smudge, requiring a dark sky and good eyes to see at all, would grow larger and brighter over millions of years, eventually becoming a major feature of the night sky. A second great band of light, alongside the Milky Way's own band. Two galaxies worth of stars visible overhead, gradually drawing closer together, gradually beginning to overlap. During the close approaches and the eventual merger, the night sky would become, by any human standard, spectacular and strange. The orderly band of the Milky Way, the familiar pale river of light that has been described in earlier explorations as the view of our own spiral arm from the inside, would become disrupted, distorted, mixed with an entirely new population of stars from Andromeda, the two bands merging, twisting, forming new patterns that no human, ancient or modern, has ever had the chance to see. Tidal tails, those long streams of stars pulled out by gravity, might appear as faint new arcs of light stretching across the sky, regions of the heavens that had always been simply dark, now hosting faint new streams of distant suns. Throughout all of this, there is a calculation that has been performed with the inherent uncertainties of any calculation, projecting billions of years into the future, regarding the probability that the Sun itself, or any planet orbiting it, would be directly affected by a close stellar encounter during the merger. The result of these calculations is reassuring, in the same gentle way that the asteroid belt's emptiness turned out to be reassuring. The probability that the Sun would be flung out of the merged galaxy entirely, or pulled into a dramatically different orbit by a close encounter with another star, is small, estimated at a few percent at most. The overwhelmingly likely outcome, for the Sun specifically, is that it continues on, perhaps nudged onto a somewhat different orbit within the newly merged galaxy, perhaps finding itself, by the end of the process, in a different region of the merged structure than where it started, but continuing to exist, continuing to shine, continuing to be orbited by whatever remains of its planets, largely undisturbed by the vast reshuffling happening around it. There is, of course, a complication to all of this, one that has stages, overlaps with another timescale already discussed in passing in previous explorations of this channel: the lifespan of the Sun itself. The Sun, a star of a particular mass and composition, has a finite lifetime, and current understanding places the Sun roughly at the midpoint of that lifetime now. In roughly 5 billion years, around the same time that the Andromeda merger is expected to be reaching its most active stages, the Sun itself will have exhausted the hydrogen fuel in its core and will begin the process of becoming a red giant, swelling enormously, engulfing the inner planets, fundamentally altering or ending whatever remains of the solar system as it currently exists. This means that the Andromeda merger and the Sun's own evolution are, in cosmic terms, roughly contemporaneous events. Two enormous slow processes unfolding on similar timescales, neither one waiting for the other, both simply proceeding according to their own internal clocks. Whatever night sky might exist to observe the Andromeda merger in its later stages would be a night sky observed, if observed at all, from a solar system already profoundly transformed by the Sun's own aging, a detail that adds a certain poignancy to the whole picture. Two vast, patient processes, one cosmic in scale and one stellar, arriving at their respective climaxes within the same broad span of time, each indifferent to the other, each simply following the physics that governs it. Turn now to the question of how we know any of this, because unlike most of the processes discussed in previous explorations of this channel, the Andromeda merger is not something that can be directly observed in progress, not in the way that, for example, the structure of the asteroid belt can be directly observed, or the Sun's oscillations can be directly measured. No human has ever seen a galaxy merger from start to finish, for the simple reason that the process takes longer than the entire history of human civilization, longer than the entire history of human existence, longer than the existence of most species that have ever lived on Earth. What astronomers have instead is something almost as useful, a kind of natural laboratory provided by the sheer number of galaxies in the observable universe. Among the hundreds of billions of galaxies that can be observed, at the staggering range of distances discussed in the very first exploration of this channel, some fraction are caught by simple chance. At every possible stage of exactly this kind of merger process, some pairs of galaxies are seen at the stage of first approach, their shapes just beginning to distort. Others are seen mid-merger, tidal tails clearly visible, stretching across enormous distances, their original spiral structures clearly disrupted but not yet fully scrambled. Others are seen in the final stages, two cores merging into one, surrounded by the debris of the encounter. And others are seen as the end result, elliptical galaxies showing, in their internal structure, the telltale signs of a long-completed merger, populations of stars with orbits and ages, consistent with having originated in two separate galaxies that long ago became one. Because the speed of light is finite, and because the universe contains galaxies at an enormous range of distances, each one showing us its light from a different point in the past, astronomers are able to assemble something like a flipbook, individual frames, each one a different galaxy at a different stage of the same general process, that when arranged in sequence, tell the story of what a merger looks like from beginning to end, even though no single observation has ever watched one merger proceed through all of its stages. The Milky Way and Andromeda, in this sense, are not unique. They are simply one example, observed from the inside, of a process that has happened and is happening and will continue to happen the universe, on a timescale that no observer anywhere has ever been able to watch unfold in real time. There is something worth holding gently here, a continuation of a theme that has run through several of tonight's predecessors. The dark night sky, considered on an earlier evening, told us about the age and expansion of the universe through the simple fact of its darkness, evidence written in absence. The asteroid belt told us about Jupiter's formation through the simple fact of its emptiness, a record written in what was prevented from happening. Tonight, the Andromeda merger tells us something through the simple fact of its slowness, a story written not in any single observable event, but in the patient accumulation of small gravitational influences across spans of time that exceed not just human history, but the history of life on Earth, exceeding even, in its full extent, the remaining lifespan of the Sun itself. In each case, the universe reveals something not through drama, not through sudden events, but through the quiet, accumulated consequence of physics operating exactly as it always has, for far longer than any observer could ever wait to watch it happen. The Andromeda merger is, in this sense, simply one more example of the universe's preferred timescale, a timescale measured not in moments, but in the slow turning of structures so large that their motion, even at speeds of over 100 kilometers per second, takes billions of years to bring about anything resembling an event. Now widen the view once more, the way previous explorations have widened theirs, zooming outward beyond even the scale of two merging galaxies. The Milky Way and Andromeda, along with a number of smaller satellite galaxies, including the Triangulum Galaxy and a collection of dwarf galaxies orbiting both larger ones, together make up what astronomers call the local group, a gravitationally bound collection of galaxies spanning roughly 10 million light-years. The eventual merger of the Milky Way and Andromeda is, in this larger context, simply the largest single event within this local group's own long, slow history, a history that will likely also eventually include the absorption of the smaller satellite galaxies, drawn in over time by the gravity of the larger merged structure. Beyond the local group lies a still larger structure, a vast collection of galaxy groups and clusters spanning over 100 million light-years, with the Virgo cluster, a massive collection of thousands of galaxies, as its dominant member. The local group, including the future merged Milky Way Andromeda Galaxy, is itself slowly being drawn toward this larger structure, part of a flow of galaxies moving toward the greater concentration of mass in the Virgo cluster's direction, a motion operating on timescales even longer than the Andromeda merger itself, a motion that will continue long after the merger has completed and settled into its final elliptical form. And beyond even this, as discussed in the closing moments of a previous exploration, the entire local group, along with the larger structure surrounding it, is itself part of an even grander flow, a motion toward a vast concentration of mass whose full nature is still being studied, sometimes called the Great Attractor, a motion that operates on the largest scales that have any meaning at all, scales where individual galaxies, let alone individual stars, become simply points of light contributing to a much larger pattern, a pattern that, much like the spiral structure of the Milky Way itself, is built not from any single dramatic event, but from the patient, accumulated influence of gravity, acting across the largest distances and the longest timescales the universe has to offer. Gather the threads now, the way previous evenings have gathered theirs. The first thread is about the word collision itself and how thoroughly it misleads. A galaxy collision involves zero direct collisions between stars, because the space within a galaxy is so overwhelmingly empty that two galaxies can pass through one another with their stellar populations almost entirely undisturbed at the individual level, even as the overall structures are dramatically reshaped. The second thread is about scale, and about the difference between the visible disk of a galaxy and its true extent. The bright, photographable portion of Andromeda remains millions of light years away, and will for billions of years. But the dark matter halo surrounding Andromeda, invisible, vastly larger than the disk, may already overlap with the Milky Way's own halo, meaning that, in the gentlest possible sense, the two galaxies may already be touching, long before their visible portions draw near. The third thread is about timing, and about the strange coincidence, or perhaps not entirely a coincidence, that the most active stages of the Andromeda merger are expected to occur